Okay, so let's write the bound. E out of G less equal to E in of G plus the square root of 8 over n, the log of 4 times 2n to the dvc divided by delta. So I'm using the version of the bound with the vc dimension, and I'm ignoring the plus 1. Okay, so this we call omega of dvc and n. Okay, and its essential dependence is O of the square root of dvc over n log n. So roughly speaking, this contains the essential, trade-off between the VC dimension, the complexity of your hypothesis set, and n. Okay, so if you double the VC dimension, you roughly speaking have to double n to get a comparable error bar. Now, inside this bound is captured the approximation generalization trade-off. So if on the x-axis I plot the complexity of my hypothesis set measured by dvc and various errors. Okay, so then the in-sample error is dropping as you give me more and more complexity, because I have more hypotheses to pick from. Okay, and the error bar omega is growing like the square root of the VC dimension, assuming that n is fixed. So this is omega, and the bound on the out of sample error displays this kind of behavior where there's this optimal VC dimension, dvc star. Okay, and here's the trade-off, right? You'd like to get E in small, okay, because that's one of the terms, so you want to pick big dvc, but you'd like to get omega small as well because you want the link from E into E out, so you want small dvc, and that trade-off that balances the in-sample error and the bound is the approximation generalization trade-off. How well are you approximating? How well are you generalizing? Okay, now this results in sort of two modes of practice. The first mode of practice is, that you have to pick a hypothesis set that achieves this trade-off. So for example, you have to pick a hypothesis set that's small, okay, while at the same time achieving a small in-sample error. So this is just the expected behavior. You'd like to pick dvc. Now, a small hypothesis that achieves the best in-sample error, that's very simple. Here, pick the hypothesis set H, which has just one function, and what's that function? Can you guess it? Ta-da! It's the target function. Okay. Now, you will have in-sample error 0, or basically 0 if there's noise, but essentially in-sample error 0, and the tightest possible link from E into E out, the single hypothesis Hofting bound. Okay, but if you're going to pin your hopes that you can pick a small hypothesis set like this, which contains the target function for any machine learning application you have, well, you're in the wrong business. Buy lottery tickets. Okay, instead, we are in the world where n is fixed. Okay, and based on n being fixed, we say what's the link we want, and that fixes the VC dimension. So this fixes dvc, for example, at dvc star. And now the goal of the machine learning, the machine learning expert, consult with the domain expert. Think. Okay, I've got this much flexibility in the choice of the hypothesis set, so I can choose that level of complexity. So what's the best hypothesis set for the problem, for the machine learning task? Okay. In other words, you're trying to get to this. You're trying to get as close as you can to this kind of a hypothesis set, but within this level of complexity, with this fixed VC dimension. Okay, so that's that's one of the inputs that the machine learning expert can bring. The other mode in which you might find yourself, and is and this is generally rarer because usually the data set is fixed, your client gives it to you, but you might be very, very stubborn and say, I have my favorite hypothesis set, and that's it. I'm using this hypothesis set. So you have your favorite H. Now we don't usually, have the luxury to be stubborn like this. My favorite hypothesis, I'm going to use a deep neural network no matter what. Okay? So I have my favorite H, and that implies, and that comes with a DVC. So in other words, DVC is fixed. Okay, and now you need to ensure the first step of learning, E in close to E out, and so that means that this error bar has to be within some tolerance that you have set. And so that means that you have to go and then tell your client, listen, I'm going to use deep neural networks or whatever it is that's your favorite hypothesis set. I'm going to use this, and I need this many data points to succeed. Why? Because I need E in close to E out. Okay? So you fix your VC dimension, and then you pick n to get E in approximately equal to E out. And this approximately is set by you. Okay, and this picking of n is sometimes denoted the sample complexity for your hypothesis. And how big an n do you need? Sometimes it's called the sample complexity. Okay, and so let's go through some examples of that. So example. Okay, so rewriting this bound, okay, we have that, the error bar, let's call that epsilon, is equal to the square root of 8 over n log of 4 over delta times 2n to the dvc. Okay, now, you're going to pick your tolerance and you'd like to find out what n is. So we'd like to rearrange this so that we have n on the left-hand side. So n is equal to 8 over epsilon squared. I squared and pulled n over there. Log times dvc. So log of this thing is dvc log 2n. Okay, and then we have plus 8 over epsilon squared log of 4 over delta. Okay. And now let's put in some reasonable value. So reasonable tolerance for epsilon is, let's say, 0.1. For delta is, let's say, 0.1. That means that you're making statements with 90% confidence, 90% that they'll be true. And this is the link that you would like to have between E in and E out. In this case, n is approximately equal to 800. So 1 over epsilon squared is 800. So 800 dvc log 2n. Okay, plus 800 log 4 over delta, which is approximately 800 dvc log 2n plus 800 log 40. 800 log of 40 is about 4, let's say. So this is about 3,000. Okay, and typically you don't expect to be needing more than e to the 10 or 2n will not need to be larger than e to the 10, so maybe we can approximate this by 10 in the worst case. So n is approximately equal to 8,000 dvc plus 3,000. Okay, approximately. And indeed, okay, what is this saying? This is saying that the number of data points you need is proportional to the VC dimension, and the proportionality constant is approximately 8,000. Okay. Now, you can actually go ahead and solve this equation for n. This is not actually an equality. This is not an equation that tells you n because there's n on this side. So how would you solve this? Maybe we plug this in as an estimate. So let's try an example. dvc equals 3. So this guy here is approximately 27,000. That's our guess. Okay, approximately 27,000. So plug in 27,000 into the right-hand side and you'll get a new value for n, maybe 29,000. Okay, that's your next guess. Goes to a new guess, goes to another, and then plug that new guess in here, you'll get a new guess. And this rapidly converges. That's an example of what's called a fixed point iteration. This will rapidly converge to n is approximately 30,000. So our starting estimate was not too bad. Okay. dvc equals 4, you get the estimate n is approximately equal to 35,000. And when you plug in the fixed point iteration and iterate and converge, you'll get approximately n is about 40,000. Okay, and if let's try dvc equals 5, you'll get n is approximately 50,000. Okay, so let's see what we're saying. So if your favorite hypothesis set has a VC dimension of 3, for example, the perceptron in 2 dimensions, okay, the perceptron in 2 dimensions has VC dimension 3, then you need 30,000 data points in order to effectively learn that perceptron. What does that mean? In order to get your link between E in and E out of just a 10% link. So if your E in was 0.1, your E out could be as bad as 0.2. Okay. Well, it turns out that that's a gross overestimate. Gross. If anyone here has, has any experience with learning perceptrons or learning linear models in 2, 3 small number of dimensions, you know that you need, order of 100, 200, maybe 1,000 data points, not 30,000. Okay. So, in practice, so rule of thumb. Okay. So, in practice, this dependence on DVC is generally speaking correct, that it's linear. So, if you double the DVC, you need double the amount of n, and we already saw that here. But, you don't need 10,000 times the DVC. In practice, 10 times the DVC is often enough. N is approximately 10 times DVC, enough. N is approximately 100 times DVC, safe. Okay, and N is approximately equal to 1,000 times DVC, golden. Okay, So that's, but these are just, this is just a rule of thumb. Okay, can't prove it. What the VC theory says is you need 30,000. Okay, and so there's a big difference in that sense between, what the VC theorem is suggesting and what happens in practice. Okay, and when we initially said that, the VC theory, we're covering it because it's relevant to practice. Okay, so let's discuss a little bit the theory versus practice when it comes to the VC theory. Theory versus practice. Okay, so theory. The VC theory is general. Okay, and that's the relevance to practice. I need to say nothing more. It's general. Any target function, any hypothesis set, any algorithm that picks a hypothesis, any data generating process, P of X, that generates your data. Completely general. And there you have the relevance to practice. You can use this theory for any machine learning setting. Okay. Now, let's look a little bit at, where this difference between what the VC theory is saying and what, we generally tend to observe in practice. Where's that slack coming from? So let's call that the slack. So where does the slack come from? Okay, it's essentially coming from the fact that we built a theory that's so ultimately general, but let's pin it down. Okay, so I'm going to point out three main contributors to the slack. The first was, the Hofding bound plus union bound. Hofding plus union bound. Okay, so what was this doing? What essentially this did was it said, you give me a G and all I need to know is that it is from your fixed hypothesis set H. Okay, and then that holds for that G. Effectively, what I'm saying is that no matter what hypothesis you picked from your hypothesis set, this bound holds. So effectively, I'm saying that this bound holds for every hypothesis in your hypothesis set. Okay? And you might think, well, that's really overkill because, maybe I don't use those other hypotheses very often. Well, then why did you put them in there? The moment you put them in your hypothesis set, the Hofding bound says, the analysis says you might pick it. And so I've got to tailor my bound to accommodate the fact that you might pick that hypothesis. Okay. So this holds for all the hypotheses in your hypothesis set. And that's what allows us to make this claim independently of your algorithm. Because no matter what your algorithm does, no matter what final hypothesis it gives, the bound holds. So this makes it for any algorithm. Okay? And any hypothesis set within that you can construct. Okay? And for any algorithm, for any particular hypothesis set. Now, there's another place where slack occurred, which was, in the definition of this M sub H of N. Okay, the growth function. So let's think about how we define this guy. So the hypothesis set is now entering here, but the discussion holds for any hypothesis set. But what was this guy? It was, the ingenious step was to say you should look at the complexity of a hypothesis set through the lens of a data set. But which data set? Okay, and that's where we said, well, we don't know what data set we're going to get, so take the worst possible data set. Take the data set for which the number of dichotomies is maximized. Okay, so this was, the maximum. So worst case number of dichotomies. Well, why did we do that? Okay, so because we don't know the data set, and so we built in this redundant, this ability to tolerate any data set, and that gives us the ability to tolerate any data generating process, any P of X. So in here is embedded the any data generating process. So for any P of X. So we have to build in, we don't know what P of X is, and that we don't know. We just get the data. We don't know P of X. Okay? So we have to tolerate any P of X. Okay, then, we now need to analyze this guy. So we bounded this guy is, less equal to B of N and K, okay, which is less equal to, okay, so, and which is less equal to N to the DVC plus 1. Okay, now, there's a little bit of mathematical slack here, technical slack. Okay, so I'll call that technical slack. Okay, but the real slack is in here. Okay, and what is that slack? What that slack is it's saying, I don't know how to analyze this guy. This is a hypothesis set with breakpoint K. So I'm going to look at the maximum number of dichotomies that you can list without shattering any subset of size K. So in some sense, I'm looking at the worst possible hypothesis set with a breakpoint K. So this considers
assumes that the hypothesis set can implement that maximum number, whereas in practice it might not be able to. It's just got a breakpoint at k. And it's just some hypothesis set which implements a small number of dichotomies. But we're bounding that small number of dichotomies by the worst possible number of dichotomies, the maximum number of dichotomies with that breakpoint. So this, in some sense, you can think of this as the worst possible h with breakpoint dvc plus 1. So lots of worst possible, and this is what allows us to make this claim for any h. So here in is built for any h. Okay. And what about, where's the for any f? Well, the analysis didn't make any assumptions on f. F will come in when you compute the in-sample error. It's what's generating the data. So you see, to tolerate these for any's, we have to, build in slack that accounts for any algorithm, any data distribution, any h, okay? And that slack is what is showing up in this number 30,000. Okay, and what it means is that, and is it realizable? Basically, yes. Okay, so what it says is that there are machine learning problems with DVC3 where you can, carefully construct the probability distribution and the hypothesis set and, and the algorithm such that if you learn in that adversarial setup, you will need 30,000 data points to make this 0.1 link. Okay? But in practice, we don't see those, craftily constructed machine learning situations. That's why in practice, there's a lot of slack, and 100 times DVC is what I recommend. Okay. So that constitutes our study of the VC theory, and, it ultimately, there are two basic realms in which it applies. The first is that, you have n is fixed, and so you have a DVC that is required in order to get the link between E in and E out, and you need to choose the right H with that DVC. And the other realm is DVC is fixed, and you ask your client for the appropriate N. Choose N. Okay. And the VC theory embeds this approximation versus generalization trade-off. Okay, you need to approximate the data, but link from E in to E out. And this approximation generalization trade-off is so fundamental. It's always there. It's always there. As a machine learner, you always have to deal with it. It's worth spending a little more time looking at it from another perspective, and that perspective is going to be the bias variance analysis. Okay. And so it's just another way to look at this trade-off, okay, because it's such an important trade-off. Okay, so we'll erase the board, and then we will be back.